So welcome back, everybody. Today's lecture will be on the Erdos-Kac theorem and generalizations. And so I think we have all the ingredients needed to prove this theorem. I mentioned the Erdos-Kac theorem at the very beginning of these set of lectures. So let me begin by making a few preliminary remarks. That will be useful in the discussion. Given a random variable x, we suppose that these moments exist. For all r. These numbers are called moments of x. The arc moment. It's called the arc moment. Arc moment of x. And we can use somehow we could kind of combine it in some sort of generating function. So we define the what's called the moment generating function as the expectation of either tx. So this is what's called the moment generating function. Now it may not exist in the sense that it could definitely be defined in a formal series, and it may not converge. We don't worry about that. We will not be needing all these esoteric properties of the moment generating functions, and all these subtleties we will not discuss in this setting. However, let's point out that this looks awfully close to the characteristic function. This resembles the characteristic function defined earlier. As expectation of e to the I tx. Okay. So, in other words, there's only a small change. And if you think about it, this was the Fourier transform of the density function. And this is actually the Laplace transform of the density function. And indeed, tx is simply the Laplace transform of the density function f sub x. Now in the
On the other hand, if we assume, for instance, x is real valued, then expectation of e to itx will always exist, but
yeah,
e to the expectation of e to
yeah,
tx
it may not, but I'm not going to go into any discussion about that because I don't need it, firstly. So we've already computed, we've shown that if phi is the normal if x is a random variable, x is a random variable with the normal distribution, then the characteristic function was equal to e to the minus t squared over 2. We calculated this before. Characteristic function. Therefore, the moment generating function for x is just simply, I just put it there. Therefore, the moment generating function of x is there for e to the t squared over 2. And if you think about it, all the moments of the object can be derived from that on one hand, e to the tx is a simple summation k equals 0 to infinity e of x to the k t to the k factorial. So the coefficient of t to the k is just simply the kth moment. And then I can see that e to the t squared over 2 t to the 2k, t squared over 2 to the power k over k factorial. That's what it is. And therefore, this implies that if x is a random variable of the normal distribution, the moments, the kth moment, better not use that. We see that the moments are 0 if k is odd, and if k is even, it's this, we see m sub 2k plus 1 is 0, m sub 2k is equal to 1 over, so you have to rewrite this silly thing. So k equals 0 to infinity. If I write t to the 2k over 2k factorial, I should put a 2k factorial here to kill that, and then I should put a 2 to the k, and of course I've already got a k factorial. Therefore, from this I see that this moment is given by this number. The even moments of the normal distribution, in other words, i.e. 1 over root 2 pi minus infinity to infinity t to the 2k e to the minus t squared over 2 dt equals 2k factorial divided by 2 to the k factorial. And if you work that out very neatly, what you have at the bottom is the product from 1 to k. You have 2 to the power k. You can move it through, so you get all the even numbers from 1 to 2k. In the top part, you have all the numbers from 1 to 2k. So the denominator deletes all the even factors, So this is nothing but 1, 3, 5, k minus 1. Now you could also integrate by parts, establish a recurrence, and prove this by induction as well. But this is the easiest way of getting it. So these are the even moments. The odd moments are 0. And the interesting thing about the normal distribution is that it's characterized by its moments. So if I have another random variable, y, whose moments are the same as that, then I would say y has the normal distribution. The distribution function is normal. Why is that the case? Well, in some sense, it's the application of the Fourier inversion. So if y is another random variable, with moments given by this m sub k, where m sub k is as before, then the density function of y is 1 over root 2 pi k minus d squared 2. To see this, we need only compute the characteristic functions. We need only compare the characteristic functions. So x here was a random variable with the normal distribution, and y is another random variable whose moments are the same as the normal distribution. And so we look at the characteristic functions, they're the same, right? And then take the inverse transform, taking inverse transforms. Shows the densities are the same. So you could see the usefulness of the Fourier inversion theorem, using it left and right. So that's one key point that we will need in the course of discussion, that if I have a random variable whose moments are exactly the same as the normal, the density function is normal.
This should hold in a much more general sense.
Yeah, it could hold in a much more general thing. We will not discuss it now, because it'll have to do with the radius of convergence of these series, and we don't want to discuss that. Here we have a situation where it converges everywhere. Yeah, as long as the radius of, the theorem is this, as long as the radius of convergence of the moment generating function is positive, you can still squeeze this through. Okay, now I think we have, here's the strategy to prove the Erdos-Kac theorem. So recall what this theorem says, that the probability of number of prime factors of n minus log n put here omega n is the number of distinct prime divisors of n. Now, it's log n. It doesn't actually matter. That's the point. It doesn't matter, and I'm going to be sloppy with this actually, because if you try to take care of those things, it gets into too much technicalities, which may obscure the overall vision of the plan. Yeah, these are small issues. In fact, I'm going to even constrain. I'm not even going to count the prime divisors of m. I'm only going to count the prime divisors less than n to the epsilon, because the number of prime divisors bigger than n to the epsilon are only bounded number, and they were little o of this log n. They're not going to matter. So that kind of bit of sloppiness will be throughout this lecture. They're easily fixed, and I suppose not too difficult to write up. So recall last time what we had, our plan was step 1, introduce random variables xp on the natural numbers, the probability of xp equals 1 over p, and probability of xp equals 0 is equal to 1 minus 1 over p. P is always a prime for me. So this will model the probability that a random number is divisible by p. So random number, how many numbers are there up to n divisible by p? Well, the greatest integer of n over p. And how many numbers are there up to n? N. So asymptotic is 1 over p. So I'm going to get independent. These are independent random variables. And as I mentioned, they're not identically distributed. But we don't care. They satisfy the Lindeberg-Feller condition. These satisfy. And so, the central limit theorem applies. So we calculated last time that the mu sub n, the mean, so we're going to look at so I'm going to change these things in a second, but I'll just put it down for now. Mu sub n is just the mean. Remember, we calculated the mean of these things. The mean value, expectation of xp is 1 over p. So that's that. And the variance was p less than n, 1 over p, 1 minus 1 over p. So we calculate the expected value. We calculate the variance. Here they are. This is asymptotic to log n by that Murty calculation first day. This is asymptotic to log n as well, and therefore central limit theorem implies that probability of Sn minus log n divided by root log n less than alpha tends to phi of alpha, the density function, as n tends to increase. Where Sn is the sum of the xp's, p less than n. so this is step number 1. Step number 2 is on the probability space 1 to n, we introduce yp, the random variable yp, and yp of m is 1 if p divides m and 0 otherwise. Okay. So on this space, 1 to n, we introduce these random variables. And now, what is the probability that yp equals 1? So let me now, because I'm not on the natural numbers, I'm on this restricted space, I'll put a piece of n there. Okay? So the probability of yp equals 1 is the number of numbers up to n, which are divisible by p, divided by n. That's the probability. And probability 0 is 1 minus that. Now clearly, this is not 1 over p, but it is 1 over p plus O of 1 over n. So as n is getting bigger and bigger, it's getting closer to 1 over p. So the way to think about this, remember I keep saying intuition is very important in mathematical research. You have to have the intuition to drive the rigor. And the intuition is that these are the real random variables that you're interested in, and these are the ideal ones. The reason you're interested in this is because omega of m is nothing but p less than or equal to n yp of m. Because yp of m is going to be 1 every time p divides m. Therefore, it spits out a 1 every time p, so it'll spit out a 1 every time you hit a prime divisor of it. And so, if this is the function that you're interested in, but the central limit theorem as applied to these ideal random variables is what we're getting from that theorem down there. We want to somehow coerce this expression into that expression as much as possible. I mean, this is obviously the intuition that I suppose probably Mark Katz had, but then he went after, he consulted Erdos, and they went towards this classical Prüm sieve to handle all these issues. And so Billingsley, I'm supposing, was thinking that this should really be made to work like child's play. Okay. So if that's so this is what we have. So these are not random variables which are independent. And what we would like to do is we will define, that's Sn, we'll define T sub n to be summation p less than y sub t. Okay. So the T sub n of m would then be just omega of m. Define this random variable. And we'd like to figure out, we want to determine the distribution.
Sir,
Question?
sorry sir. Sir, that omega n is equal to summation p less equals to n or less equals to m, that I am unable to understand.
Because I'm only on this space, I only need to look at those. Right? I mean, m is a number here. And any prime divisor of number here will be less than n.
Okay.
Yeah? So I don't need to look at all the primes. I could take all the primes if I wanted to, but here, I'm doing it this way. Now we want to determine the distribution of T sub n. And because I know this random variable is normally distributed, it makes sense to try to compare. We want to determine this. We want to prove. Prove T sub n minus log n divided by root log n is normally distributed. That's what we know that, but we want to get this guy. Now, so this is where I want to now inject this very interesting method called the method of moments. So one strategy is, if I can show that the kth moment of this random variable is the same as the kth moment of that one, I'm getting closer and closer, and I actually want to say it's done.
Just out of curiosity, so if you just compare the error between Sn and Tn just to get a big old bound on how far Sn can be from Tn, then is it possible to show that error will go to 0 as n goes to 0?
Well, that's the strategy. Eventually it'll boil down to that. But there will be some adjustments needed, and I'll discuss that now. Yeah. So we will apply what's called the method of moments. In other words, what we will do, we will calculate for the normal as n tends to infinity. But now we have a random variable which has the same moments, not quite, tending to, doesn't have identically equal to. So let's for the sake of understanding, let's just say it equals instead of tending to. Then we're done by that remark I made. If I have a random variable whose rth moment agrees with the rth moment of the normal, then it has to be the same distribution. But here I have a limit instead of an equality. So I need a little further remark, and this I'm not, so remark. We need a little lemma. If y sub n's are random variables such that the rth moment tends to m sub r of the normal, then there exists a subsequence so let's say it this way. So with each of this, so we have this, and corresponding to each yn, we have for each yn a density function, or maybe better to say distribution function. Doesn't really matter, but anyway, distribution function. So let's see, so that I can write 5 at the end. It's a density function. Density function, f sub n, say. Then there exists a subsequence n sub k such that f sub n sub k of t tends to phi of t. That's the density, normal density for all t, wherever I am, for all t. Density for all t in the wheels. So you have this little technical lemma, which is not hard to prove. I won't be proving it, but you can see how it could help us.
This is again weak star convergence, or do you have something?
No, this is pointwise. That's the beauty of this. This is pointwise, and you know how actually the proof is cute. So what do you have? You have a sequence of distributions, right? So this is a very clever argument of Helly. So it goes under the name of Helly's selection principle or something. So I'll tell you in 2 sentences what the strategy is, and you can at home fill in the details. The idea is that we have Fn as these density functions, and what you would do is we have you more or less say, suppose that these density functions are compactly supported. They're not, but essentially they are, because of these finiteness of these moments. Okay, so let's not worry too much about that. They're compactly supported. So what you do is, in that compactly supported, let's say, finite interval, you take all the rational numbers, and let's just make a listing, R1, R2, etc., etc. So for the first R1, you have the sequence Fn of R1. Fix R1. And now you have Fn of R1. It's a bounded sequence, and you have this Bolzano-Weierstrass theorem that says there's a convergent subsequence. You take that, and you write that down. Now you have now these functions Fni of x's, a new set of functions now, and at R1 it's fine. Now you do it for R2, the next rational number. You do, and then you have this diagonal argument, and you go through this Cantor diagonal argument and construct this function. Once you have the idea, it's clear, but to write down all the details take me time, but I'll just leave it at that. So this is what's called the Helly selection principle. Okay, so there is a subsequence on which it happens. Therefore, I know that the moments are tending to MR, but there's a subsequence of density functions that are pointwise doing this. Therefore, the corresponding moments are tending to the rth moment, right? These guys are also tending to the rth moment. And then these functions, because it's a convergent sequence, this actually tends to a limit. This this actually tends to limit, and that limit function is the distribution that I was after, which has the property, the corresponding random variable for this. What do we have? We have so take a random variable, let's use a different notation, let's say y. Let's take, this is the density function I would get, and I would take this random variable y, which has this density function. The rth moments of this match up with the rth moments of this. Therefore, the distribution of y must be the normal, and that's how you end up getting it. So, let me just point out that it suffices therefore to show this modulo this Helly selection process. Okay, so once we have, we can show these moments are also going to R, m sub r, we're done. So, and this is, as I said, this is not hard, this business is not hard. Okay, so we'll just leave it at that.
Then won't you only get a subsequence for which you have the distribution? So
Yeah, no, we have a subsequence, and from that, not subsequence, we get this f. And then we have y, and then yes, on the subsequence we have that the moments are identical, but remember, originally the sequence of moments tends to MR, and if the subsequence tends to MR, then for if this sequence is tending to MR, on that subsequence, the moments must tend to MR as well, and I apply it to this to get my hands on the density function. And that density function must be the one that I'm after. That means corresponding to this particular random variable, I would have the appropriate distribution.
So basically you're saying that since the moments are, since the expectation of y into the r is converging to mr, you have a limiting distribution.
Yeah.
And since you have a subsequence is converging to your whatever you want, you're also concluding that the limiting distribution is what you want.
Is what you want, exactly, yeah. So, let me just say then, since we already had Sn minus log n over root log n tending to the normal, it suffices to show that I have this happening. Once I have that, then I'm just saying I'm done, modulo this business. So, I hope everybody understands what we know that the expectation of Sn minus log n over root log n our r tends to n sub r. We know this. That's the central limit theorem. What we don't know is this, because these T-ants were not independent, they're not identically distributed, nothing. So we want to get there, but Sn looks awfully close to Tn, and we're going to play a game of approximation, as you were suggesting. So in order to facilitate this calculation, let me say that we want to show this for every r. We want to show this for every r. And we know this for every r. So fix r. Fix an r. We want to show this, right? Now, once I've fixed my r, I want to show this. Therefore, I'm going to do some tampering. I'm going to change this to n to the epsilon. Epsilon to be chosen sufficiently small to depend on r, but we'll worry about it later. The reason I do that is because in both cases, the things which are bigger than n to the epsilon is just all one. Epsilon is a fixed quantity. So we will do this small modification and prove the theorem of this. Now, we already know this. So So I'm going to put this here and look at the difference. So fix R, take epsilon positive, to be chosen later, and consider the difference between these two. If you don't mind, I'm gonna change the, let me just call this, abbreviate the notation. Mu sub n is log n, and sigma sub n squared is log n. Okay, so then I can have mu n over sigma sub n to the half. Consider this difference. This difference. So
You have 1/2 sigma to 1/2, what is
Sigma n.
sigma n to the, yeah, sorry, that's sigma n. This sigma n, thank you. So Sn minus mu n over sigma n to the r is something I know is mr, it is tending to mr. So I'm going to consider this difference and show it goes to 0. Consider this, and the question is, does this go to 0 as n goes to 2? That's what we'd like to show. So let me keep this. As well as that. And now, what is Sn? Well, what do we have here? So let's look at the left-hand side. Let's look at this expression here. So we want to show this goes to 0. We fixed the r. We've taken the epsilon, which will depend on r eventually. And then we want to show this goes to 0 as n goes to infinity. And if you look at it very carefully, you'll see that you can expand this in terms of binomial coefficient. So this is essentially boils down to expectation of summation r choose, make sure that I didn't use k yet, okay, k, r choose k, Sn to the k, mu n to the r minus k, divided by, well, this sigma n to the r is just common, so I'll just put it over here. K going from 0 to n minus Tn to the k mu n to the r minus k. This expression is nothing but this. And I want to show it goes to 0. This k equals 0 to r. Okay? So keep in mind that r is fixed in this k, and so the expectation moves through. And since r is fixed, it's a finite collection of these expectations. So we need to, it suffices to show the expectation of Sn to the k minus Tn to the k use of n r minus k. This is just a number. This comes out. Okay. And that goes to 0. This mu n to the r minus k is just a number, but I'll need it. I can't throw it out. Sorry, there's a sigma n to the r here. There's a sigma n to the r down there. I should put it in here. Now keep in mind that essentially, what do we have? Mu n is log n. Sigma n is square root log n. So square root log n. So basically what we have here is, if I will do some overkill. So in the worst case scenario, k could be equal to r, and therefore
mu n is same as sigma n, right? Mu n is same as sigma.
I know, but yeah, we'll keep. Yeah, but yeah, that's right. So the worst case scenario, this could be just 1. So it suffices to show actually that
I mean, sigma n and this is log n.
expectation of Sn to the k minus Tn to the k. Sigma n to the minus r goes to 0 and then goes to 1. It suffices to do that. Yeah, you're right. So then they disappear. Right? Then this.
I was wrong.
Sigma n square root of
Sigma n is square root. Yeah.
Yeah.
So they don't disappear. You guys are supposed to help me, right? That's right. So you have a square. So essentially, therefore, we have. If you think about it, mu n essentially is sigma n squared. So this is essentially what we need to do is mu n to the r over 2. Show that that goes to 0. Okay. I hope everyone's following what I'm doing. Yes.
Is not that minus mu n to the power r minus the very last line?
Here.
Yeah. That minus mu n.
Mu n to the r minus k.
No, that is
minus
expansion.
1 to the power something.
Minus a minus b whole to the power. So we should have minus mu n to the power r minus.
Oh, there's a minus sign, you mean?
Yeah.
Oh, yeah. There's a minus sign. You're right. There's a minus sign. Yeah, but the minus sign.
No, I am saying minus mu n whole to the power r minus k. No?
Go here. Yeah.
You will have Sn minus Tn, but there will be a minus that is coming out of everything, depending on k.
Yeah. So you're right. So I'll put it this way.
No, sir, minus should
No,
come
I know.
out,
I know
sir.
what he's saying. I
Yeah,
know what he's
yeah.
saying,
Yeah.
So
That's the-
r minus k, mu n, r minus k. Is that what you're saying?
Yes, sir.
Yeah. No, I've got to set it up right. I don't want to get the signs all messed up. This is easy, but you just have to keep track of all the calculations. Okay, so this is where now you've got this guy. So I'm saying, remember, I keep using this word. It suffices. I'm not saying it's equivalent. It suffices. So if I can focus my attention just on this silly difference, I'm done. And that's what I want you to understand. Sn was the ideal one. Tn was the one that I was interested in, and I need to make sure they're, and so what it's boiling down to is this calculation. wouldn't matter, this sign goes outside. And as long as I show each piece is going to zero, end of
Yeah.
story. I don't need to worry about the sum, yeah. And I want to reduce it, and I'm gonna say this is going to be a triviality now. Once I understand what I have to do, then I'll realize it's already done. Okay. So, what is this? What is this? Well, what is it? Sn, remember, is this. Tn is this. And so it's got a bunch of, it's like a multinomial theorem. And so what do we have here? We have expectation of this summation x, so we have a multinomial theorem, which we'll use. I'm taking the kth power, and so it'll be j1, jk. So I've got, x1, x2 plus x3 plus x5 dot dot dot, a bunch of these guys, and I'm raising it to the kth power. And so this is the multinomial coefficient, and I'm going to pick up xp to the j1, xp to the, xp1 to the j1, xpk to the jk from the first guy. And then times this mu sub n to the r over 2. You'll see that this is irrelevant at the end, but let's keep it there. Does everybody see what I've done? This is the multinomial theorem. So j1 jk, j1 to j. Let's just put u, not jk, j1 to ju. So this should be p1 to pu, j1 to ju. So another variable here. It may not be k primes. It might be a bunch. Let's say there are u primes in there. U would be the number of primes of that thing. But the fact of the matter is, this is the term, and keep in mind, the sum of the ji's is k in this multinomial business. The sum of the ji's is k. Okay, now, again, keep in mind that r is fixed. And what was k? K was less than r. So this expectation moves through, and I have to now analyze the difference. Expectation of xp1 to the j1, xpk, pu to the ju, minus expectation of y, p1 to the j1, y, pu to the ju. We have to study this. Okay? Keep in mind that the random variables that I have, whether it's xp or yp, they only take on two values, 0 or 1. So there's really no point. Xp to the j1 is the same as xp. There's really no point in taking these. We've simplified life even further. Now, these are independent random variables. So the expectation of is just a product of the expectations. So this is nothing but 1 over P1 to PU. So it was independent. These guys are not. What is now? Keep in mind also we have to have we have to worry about distinctness. Okay, so we're going to assume that the P1 to PUs are distinct. There could be duplicates, but I've combined them all in some sense. Let's not worry too much about that. But anyway, let's say these are distinct. P1 to Pi distinct. Let's say P1 less than P2, just to get the order right. And then I may have a factorial, U factorial. But keep in mind that U is a parameter which is less than K, and so it's everything does not depend on N. Because I'm going to be taking limits as N goes to infinity. So this guy is counting how many numbers are there less than N divisible by P1 to Pu. Well, I know how many there are. That's right. 1 over N, N over P1 to
N power epsilon?
No,
No.
we don't bring that in.
That's it.
We don't bring that, yeah, we don't want to count, we'll worry about that n to the epsilon later. I'm just saying, you know, their primes are under this constraint, but I have, when I choose the primes, they'll just have to be less than n to the epsilon. Yeah, we won't worry about that. So this is what this difference is. But this difference, as we agreed, is big O of 1 over n. So it's big O of 1 over n. This stuff here is big O of 1 over n, comes out. And what's left is a summation over all these possible primes. Because remember, this is for each prime, where each choice, the summand, when I push the expectation over, the summand is O1 for each choice of P1 to Pu. How many choices do I have? Well, as many primes, now your n to the epsilon comes in, as many choices as I have for this. Well, let's just overkill. How many choices do I have for the prime Pi? N to the epsilon choices. How many, I'm taking the kth power. K is at most R. Therefore, the number of summands, so each summand in this calculation, each expectation is O of 1 over n. So, if it's O of 1 over n, I push the 1 over n outside. And then I have to now count how many P1 to Pus am I making the choices for. Well, the choices for the Pi's are at most n to the epsilon, right? And therefore the number of summands is n to the epsilon to the power r at most. And then remember, I have a 1 over n from here. There's a 1 over n that came, taking into account the discount, taking into account the discount of 1 over n, you get 1 over n to the epsilon r. Because remember this difference, when I pushed the expectation, we agreed this difference was O of 1 over n, push it outside. Now count the number of summands. The number of summands is n to the epsilon r. And so the final contribution is this, times this mu sub n to the r over 2. Hmm?
1 by n is big O of 1 by n?
Yeah, big O 1 over n, yeah. So now, yes, you're right, big O. And now the question is, I could have picked, remember my epsilon was up to me to choose. I'll make sure epsilon is strictly less than 1 over r, yeah. Then so that I have a saving, and this is just log n, this goes to 0. End of story.
What was the last?
I choose my epsilon to be less than 1 over r. So that this exponent n to the epsilon r is less than 1, which means that when I divide by n, I've got something less than 1 minus 1, which is negative. Therefore it goes to 0. And the power of n, this is only log n to some power. It doesn't matter, it goes to 0. Yeah.
How did you get the number of summands?
The number of summands is, well, with the number of choices, you see there should have been a sum there should have been a here, a sum over the P1 to PU, right? So I have XP1, XP2 up to XPU, whatever the XPIs to the power K, and I have to choose the primes, right?
1 to R.
Yeah, so, yeah, exactly, so I have to choose the primes, so I choose them, and, the number is at most, the number of primes is at most, the number of summands is at most 10 to the epsilon, that's overkill.
And then you have to make R
The
choice.
number of P1 to PU will be, for each prime you have n to the epsilon for this, and the number of.
No, not for each prime I have into the epsilon choices. I'm saying, so this is a summation over P1 to PUs,
Yes,
and where they've been picked out of here.
yes.
Okay, so I have some, XP1 plus XP2 up to XPU, say, or something, to the power R is a typical or largest. So when I do that, I've got a multinomial thing, and I've got to choose in these R things, so it's a product of R things, right? Each time I'm making a choice of the PIs. But the choices of PIs is at most under the epsilon. And there are at most R choices I'm making for each factor. So in each factor, there are n to the epsilon primes at most. And there are terms, because it's an rth power, and therefore n to the epsilon to the power r. Which is what I got here.
I think that means that less or equal to n to the power addition.
Yeah.
Yeah.
This summand is less or equal to this thing.
Yeah, it's less than, it's all less than, I'm not saying it's exactly.
Yes.
Yeah, this is why this O notation is very important, you see, this O notation, this estimation, this is an important feature in analytic number theory, which is not shared by algebraists. The idea that somehow you want to get the asymptotic behavior and you are kind of, sidetracked or hijacked by these itsy bitsy irrelevant considerations of whether this thing is like, so the big O notation just throws that away. Just simplifies life. It's good to get used to the notation, yeah. Okay, so that's it. This is the proof of the Erdos-Kac theorem. Now let me point out.
This is sort of this n to the epsilon trick is an analog of putting your exponential minus, within the calculation of Fourier transforms and so on.
Yeah. It's, I mean, Erdos was very good at that. He knew exactly where to break these things up. Yeah, this n to the epsilon trick is a good one, and instead of trying to count all the prime divisors, you just truncate it, and then use this truncated trick. Now, anybody who has been observing carefully this proof sees that there's a lot of freedom. For example, I could have chosen epsilon really, really tiny, and like 1 over r squared for all I care. Okay? So that essentially I've got a 1 over n, which of course goes to 0. So there's a huge amount of saving in this argument. Okay, so when you study something like this, you realize definitely this is a special case of something general. And so that's what the content of my paper with Kumar and Sudhir Puja Hari called the all-purpose Erdos-Kac theorem. Okay, so let me try to explain that in the last 30 minutes. So this suggests an all-purpose Erdos-Kac theorem applicable infinite subset of the natural numbers. S could be the natural numbers, S could be primes. In the two examples I will give at the very end, those are the two. It could be other things too. Then, for each M in S, suppose we are given an integer a sub m, like so, a sub m not 0. Let's not worry about the 0 business. Some number. For each m, we have a number a sub m. We assume the following. 1, a sub m is equal to O of m to the a for some a. In other words, doesn't make positive, but the growth of the sequence is polynomial, not too large. Okay? Second, for each square free d, we write SND to be the number of m such that d divides a sub m. And suppose that SND equals delta of d s of n plus little o of s of n, where s of n equals the number of m less than or equal to n and s. Okay, so the number SND is the number of elements in S such that D divides A sub n. Number of elements M such that D divides A sub n. So we assume that. And we need to some technical condition. We need lim sup delta of L. L is prime for me now. L prime. We need lim sup to be less than 1. Don't worry about this condition. This is thrown in for technicalities. And finally, number 4, for any p there exists a theta such that so d is square free, so I'm going to put that as d less than n of theta s n d minus s of minus delta d s of n is less than or equal to some constant k s of n over mu sub n to the b, where mu sub n equals summation L less than n delta delta. So in order not to explain what the constants are, sometimes we use what's called Vinograd notation, just big O notation. It's nice to have this extra notation. You could say big O of that, but sometimes it's neither to say it like this. This is the same as big O notation. In other words,
Assuming that delta is multiplicative or something?
I don't need that. No, I don't need that.
What is delta here?
Some number. It's like a density. Yeah, so I think you're right. We need multiplicativity. So here, when I define delta, delta is some number. Delta is a multiplicative function. So what is a multiplicative function? F of mn equals f of m times f of n whenever m and n are also prime. That's a multiplicative function. Okay, so we'll need that, yes. So with these axioms in place, notice by the way, for those who are familiar with Bombiri-Vinogradov style theorems, usually in these Bombiri-Vinogradov things that you ask for a saving of arbitrary powers of log here. So here, we're asking for arbitrary powers of this mu n. Now in practice, delta L is 1 over L. L is prime. Therefore in practice, mu n is usually going to be log n. So unlike the classical Bombiri-Vinogradov setup, this is weaker. So it suggests maybe some hope of proving, having this satisfied in many cases. So under these conditions, when we have these conditions, so supposing I have all these conditions satisfied, then we have an Erdos-Kac theorem.
You don't have to go up to half.
No, use any sums, any itsy bitsy theta is good. It's that n to the epsilon argument. That's why there's a saving, right? Then the probability of omega, so m, omega m, omega a sub m minus mu sub n divided by, so basically what we have, sigma n squared is going to be delta L 1 minus delta L. So you got a general theorem, doesn't matter what sequence you have, as long as the sequence satisfies these properties. Now let's just see quickly applications. If S is the set of all natural numbers, go back to the Erdos-Kac. This is all the set of all natural numbers. And for each natural number, I'm going to take the natural number itself. A sub n is simply n. A sub n is simply n. And then I have to ask myself, is it polynomial growth? Yeah, m is O of n, good. What do I have here? I have to check how many numbers are there such that d divides m. That's n over d. So delta of d is 1 over d s of n plus O of, O of 1 actually. Okay? And so that's pretty good. Little o, this I explained little o before. And lim sup of the delta L's, of course, lim sup of 1 over L is 0, less than 1. And as I told you, this is a kind of a technical condition, so don't worry about too much about that. And then the question is, what in here we have to check for? What do we have to check? We have to check how many numbers are the SND equals n over d, isn't it? That's the number of numbers which are divisible by d. so that's equal to 1 over d times n, which is S of n, plus O 1 over, yeah, O of 1, O of 1. Okay. And so the difference between this and n over d is O of 1. And what do I need? I've got, looking at all the d's up to into some theta, better come up small. So it's O of 1. What's the estimate? O of n to the theta. What do I need? I need n over log n to arbitrary power. Oh, it's all overkill. It's definitely satisfied for any theta less than 1. Doesn't matter. So clearly, this gives Erdos-Kac. Okay.
Can you hope for a faster rate of convergence than?
Oh, those are good questions. Faster rate of convergence, you mean at this stage?
Yes.
Oh, those are good questions. In fact, that's a good topic for research. Nobody has studied that. Even in the classical case, I think the only person that seems to have looked at it is William Levesque, who was a student of Mark Katz, and he looked at rates of convergence. And I don't think other people have looked at it for other problems. Hmm? Well, whatever. Yeah, some people may have looked at special cases.
What about shifted primes do you get?
That's why I'm coming to that. Yeah. So number 2, shifted primes. Now this is Halberstam's PhD thesis. So he shows that omega of p plus a minus log p over root log p probability n prime less than n less than alpha tends to the normal. To prove this, now this is an interesting thing. He proved this in the 1950s. It's in 3 papers, and they're messy papers. They're pretty ugly reading. Part of his thesis. Now, any student who's interested in SIP theory, I would recommend reading that paper, those papers. The reason is because this was before the Bombay-Vinogradov theorem. So let's see how we can get this from our axiomatization. So in that case now, S is the set of primes, and for each m in S, that each prime, I have to give you a number. I'll give you p plus a, okay? P plus a. And then of course it's polynomial growth. For each, I have to count the number of primes such that p plus a is divisible by d. That's the same as primes congruent to minus a mod d. And we all know about that. Pi of n divided by phi of d. So delta of d will be 1 over 5b. And then certainly the number 3 satisfied. And now we come to here. We come to primes congruent to minus a mod d minus the expected thing. We want it to be small. And those who are familiar with the Bombay-Vinogradov theorem knows that this gives it to you very quickly with a theta. Any theta less than a half will work. But Halberstam didn't have Bombay-Vinogradov theorem. And he repeats the Erdos-Kac mess, sieving this, sieving that, Brun sieve. So I'm sure if he had stood back and looked at what he's doing, he could have seen the Bombay-Vinogradov theorem in there. So there may be something to be studied there. There are 3 papers. So you easily get, so somebody's, you know, 3 papers just fall out of this whole setup. Next, yeah, I've got 10 minutes left. Next, let's have a look at a few more things, which are basically my students' works. Oh, one more thing before I continue, which is again Halberstam. And I think this has to do with, supposing I have a polynomial f of x with integer coefficients, and I want to count how many prime divisors are there of f of m. So, let's look at that. Here, again Halberstam. Again, I think it was his thesis that he did. Take a polynomial f of x, and we want to study omega of f of m, number of prime divisors of f of m. And so we ask ourselves, so here S is natural numbers, and for each m in S, a sub m is f of m. We have to then ask ourselves, are these axioms satisfied? Well, yes, it's polynomial degree. For each square free d, we have to check how many numbers are there less than n such that f of m is 0 mod d. And it's for square free d. I need to know for square free d what's going on. Now, square free d mod d, Chinese remainder theorem, right? So this is equivalent to counting for all primes dividing d. I need to check m, you know, I need to examine the congruence f of m equals 0 mod p. Modulo p, f of x equals 0 has finitely many solutions, residue classes, let's say t residue classes, and that means I have to count how many m's are there that fall into those residue classes mod p for every prime p. So it's easy calculation, and when you do it, this is easily satisfied, and I think I'll leave it to you to check that number 3 and number 4 also satisfied. You get Halberstam's other paper. I think that's, so we're now 3 papers that deal with the shifted prime situation, and 1 paper that deals with the polynomial. So 4 of Halberstam's papers will just come out of this thing. Good. So back in 1983, I think, Kumar and I were looking at Fourier coefficients of modular forms. And here we were interested in, well, instead of trying to give definitions of modular forms, let me just look at the Ramanujan tau function. So this object, if you take this power series, so take this infinite product and expand it as a power series, you end up getting what's called the tau function. So that's the definition of the tau function. It's a bad definition, but it's the fastest. And the question is, can we study omega of tau n? And can we study omega of tau p? Okay. Now let's not worry about this. I'm not going to talk about this because it's hard and it does not fit into the scheme. but the second one does. Firstly, tau of p has polynomial growth. I think most of you know that. So that's a sequence. It's very close to this shifted prime business. The set S is the set of primes, and for each prime, I'm going to look at tau p. And so I have polynomial growth, very easy to prove, not too hard. For each prime, for each d, I have to know how many primes are there such that d divides tau of p. Okay, that's the million-dollar question. Oops. And so we come to atal cohomology. Okay, we come to atal. Actually, that's not making it up. So in Deline's work, the homology conjecture. The homology conjecture is that for any prime p, this is 2 to the 11 halves. So this is an interesting conjecture that Ramanujan had made, and many people thought that it's just a curiosity, and until the 1950s, when it started showing up as a deep problem in algebraic geometry. And somehow, if you solve the problem in algebraic geometry, you end up getting this. And that's what Deline did. He solved it in the late 60s, and showed that there exists a Galois representation so if you don't understand all these words, it's okay, it's almost at the end. Into the Elatic integers such that rho L of sigma p, since Krishnarjun defined sigma p in yesterday's talk, I'll just use it. The trace of this, it's a 2 by 2 matrix. The trace of that matrix turns out to be tau of p. Sigma p is an automorphism in the Galois group. And so what does this mean? It's sending group elements to 2 by 2 matrices. That's what this representation is doing. And the amazing theorem of Deline is there exists such a representation such that the trace of this Frobenius automorphism turns out to be tau of p. Now with this, there's a whole section of algebraic number theory associated to Artin-L series that allows you to study, now, change questions about divisibility by, let's say, L to the study of sigma p lying in a certain conjugacy class in this Galois group. And so you can bring in what's called the Chebotarev density theorem.
I think you have to be careful when p is equal to L.
Of course. We don't worry about things like that. I'm not, okay. So we have to use this Chebotarev density theorem, which allows us to tick off this number 2 and say, yes, we have this. So it's again a Chinese remainder because d is square free, so you have to do it for all the primes, and then using this representation, you can answer this question. You can certainly answer this. It turns out that's fine, and the hard part is 4. When it comes to 4, we assumed GRH, or what would be called quasi-GRH. You don't need the full GRH as you are understanding it now. You just need some theta. And so a quasi-GRH, the Chebotarev density theorem, will allow you to ensure number 4. And then you would get that the probability of primes less than n such that tau of p has prime divisors, etc., is the normal again. But unfortunately, it's a conditional theorem. And it's not terribly onerous to have this because it's not even asking for power saving or log, arbitrary powers of log, but really log, and so there may be some hope. So this could be an avenue of further research. We don't know at the moment. And so that's where it stands. I'm running out of, I've run out of time, so maybe it's a good time to stop. The axiomatization is good for this, but it's not good for this. And it may be further work is needed in order to understand that because our earlier work was lengthy. So I hope this gives you a good understanding of how you can look at these proofs. It's important not just to prove theorems, but to understand how the theorems are proved. And there is, as Artin would say, there is an elegant proof versus an ugly proof. An ugly proof is not desired, but an ugly proof is a proof after all. And therefore, an ugly proof means that there has to be a beautiful proof somewhere. And you should look for the elegant proof. So when I first came across Billingsley's paper, I knew this is something that is very neat and clean and probably can be used in a wider context. And that's what motivated our work. So this more or less ends my section on Erdos-Kac and generalizations. So we will leave it there, and tomorrow I will try to introduce how probability theory is connected to sieve theory and answer the question, if I take a polynomial with integer coefficients at random, is it reducible or is it irreducible? And the answer is going to be that it's irreducible with probability 1.
Probability 1.
Probability 1. How would you prove that? That's tomorrow's.
As that this condition 1, 2, 3, 4. So this is from your paper.
Yeah.
So now I think it's. I mean, one can take that how much this condition we can use in more general context to prove, which is something already have been proved, but we can look again and see if these 4 conditions satisfied, then we can conclude something.
I don't quite understand that statement.
For example, you these 4 conditions, from these 4 conditions you are applying to Deline's proof, and you are
No. These 4 conditions apply, then the result of others coming, new also you can produce if you can get hold of some nice set S and AMs.
Yeah. So the sequence has to have these properties.
Yeah.
The sequence of A sub m's has to have some structure that you have some control over. And the control is only about divisibility. I'd like to know how many numbers in this sequence are divisible by D. Just like how many numbers in the natural numbers are divisible by D. It's n over D, right? That was that. But here, I'd like to know how many they are, and some hypothesis is needed. So what did I do? I went back to the Erdos-Kac proof and axiomatized and tried to say, what is it that I'm using at every stage? This is the method of abstraction. You ask yourself, what is it that I'm using at every stage that is not necessarily peculiar to the problem at hand, but will apply in a more general context? So once I isolate those things, then I can axiomatize it. And once I've axiomatized it, I have a general theorem, and you don't have to keep on reinventing the wheel each time, which is what was happening for the last 50, 60 years. Because Halberstam wrote umpteen papers, people wrote papers on other things. I didn't have time to talk about other questions, but there are more applications of this stuff. Yeah.
Are you assuming tau of p is non-zero?
Yeah. No, we're not assuming it. We're just throwing them out first.
Okay.
See, there's sparse set of primes.
So you're using Sayre's result and assuming that it's
Whatever. Yeah, okay.